covered from last week. It's a pleasure to introduce Mike Teper from Oxford, who will tell us about QCD strings from the Lattice.
All right, thanks, David. It's a pleasure to be here, and it's nice to see everyone here at 8:30 in the morning. So I checked out with some of the people who were here earlier whether this one or this one was better, and turned out that despite the fact the light here is slightly dimmer, it's better, it's easier to see. So that's why I mostly use this side and the blackboard. Okay, this what are these lectures about? Well, it's the what I'll try and do is to tell you something about what we're learning from lattice calculations about the limit of large number of colors, so SUN gauge theories for large N. And I'll try to focus on those things which fit in with some of the other interests in this workshop at this time, which is to say strings and ADS CFT. So I'll focus on those aspects of the subject when during these lectures. So there'll be a kind of preamble which is going to consist of telling you something about lattice calculations. Now, with some analytic calculations, you can present them on the blackboard, the details. With a lattice calculation, obviously I can't really do that in an effective way, but what I can do is to describe you how the lattice calculation works in general, and also in the particular cases where I'm applying it, what are the, if you like, the uncertainties. So, you know, when people do lattice calculations, they present you with some numbers, and like experimentalists, they put some errors on those numbers. But just as with experimentalists, there are other errors that you don't always mention, which are not the easy ones to calculate. They're the ones called systematic errors. If you could calculate them, you would, and they would be there as a number, but you can't, so you estimate them somehow and talk about them as systematic errors. And so I'll try to also tell you about those kind of errors, if you like, or uncertainties in the calculations, so that you can perhaps have some feeling afterwards what is the, you know, how these calculations can be improved and how much you can trust them. So if we're talking about large N gauge theories, or the large N approach to QCD, then the first big question is large N at all relevant to QCD, SU3 gauge theory, the underlying gauge theory of quantum chrome dynamics? And so that's a question of whether, in some sense, is n equals 3 close to n equals infinity. So that's one thing we would like to see within the lattice calculations. Is that the case or not? And then the second thing is most of the apparent similarities between features that you can qualitatively argue for at n equals infinity and ones in the real world in quantum chromodynamics, of course, depend on the idea that at n equals infinity the theory is still confining. So one of the things one would like to check is whether when one increases the number of colors, whether the theory remains linearly confining. So those are the two initial questions I'd like to address, and that will take up quite a bit of today, I think. Then the other two main topics I'd like to talk about are, first of all, the thermodynamics, SUN gauge theories. What do we know about SUN gauge theories from the lattice at finite temperature? Because this matches on with a lot of the current work from the ADS CFT side, which comes in above the deconfining temperature and tries to say something about the deconfined properties of QCD. So that's why I particularly focus on that topic. In addition, of course, it's of real physical interest because there are experiments that have been going on trying to probe that regime of quantum chrome dynamics, and there will be more experiments at LHC with the Alice detector once LHC is running, which I understand there's some further delays, but no doubt by the end of next year, middle or end of the next year, everything will be going. So that's the second main topic. And the third main topic is strings. So we have linear confinement in quantum chromodynamics. So we believe, we can't prove that, but we believe that's the case. And part of the reason we believe it, part of it is phenomenological, and there's some arguments from what you observe in the real world. And then other reasons are to do with lattice calculations, which show that if you take static sources in the fundamental representation and you move them apart, the potential grows linearly with distance. So there's a lot of evidence that we do have linear confinement in that sense in gauge theories. And once you have things growing linearly with distance, you have the idea that the flux is in a flux tube. And if you have a flux tube, then once the flux tube is very long, it looks like a string. And then it should have some of the properties. It should be perhaps be described by some effective string theory. So one of the things I'll be doing is looking at the spectrum of closed strings and seeing to what extent it looks like what you might expect from an effective string theory, or indeed the simplest Nambu-Goto string theory. So those are the three main topics I want to address. There's a few others that I'll sort of probably manage to say something about some of these if I have time. So I definitely want to say something about K-strings, which are strings which join sources in higher representations than the fundamental, because that fits in very well with the main topic of closed string spectrum and has some important extra things to say about the string spectrum. Then something that perhaps lies a little bit outside these other topics. There are interesting things about the topology of gauge fields and interlacing theta vacua, and some work has been done on that on the lattice, so I'd like to mention that if I have time. And also there is a very interesting approach to trying to solve analytically D equals 3 SUN gauge theories by Carabali and Nair, and they get results which are very close to the lattice string tensions, and for that reason one would like to do a very accurate comparison, and that's what we've been doing. So I might say something about that. And another topic of interest is the twisted Oguchi-Kawai space-time reduction, which is an alternative way of going to large N. And I'll mention something about that right in my introduction. But that's an interesting topic which I may or may not have time to discuss. But if you want to know about it, someone who's a couple of people here who've worked a great deal in the past, Pierre Bambal has worked a great deal on this, and more recently my student Helvio Varinos, who is here somewhere, has also done his thesis on this and learned interesting things about the utility of twisted Oguchi-Kawai models. So you can talk to them if I don't have time to talk about this. Okay. Before continuing, let me just say that there are a number of people who've been working on this. The sort of a large N, most of the work, of course, as you might imagine, that's been done by lattice people over the last 25 years or so, has been aimed at QCD and learning quite naturally about the properties of QCD directly. Looking at large N is a topic that which I started doing in the 90s and produced some results about the same time as ADS-CFT produced their approach, and so there was a kind of nice merging of interest at that point. So it's a subject that's been going on for about 10 years in its modern form. In the early 80s, right at the beginning, when people first started doing lattice simulations, there was some work, attempts using the twisted Oguchi-Kawai, but in retrospect, for reasons that will become clear if I do get around to discussing that topic, most of that work was probably optimistic. Okay, so, but there are some other, okay, so let me just give you, since I won't refer to systematically to different groups, let me just mention some of the people who've been involved in working on large N in the last 10 years. There is what I loosely call the Oxford group, which is not really any more Oxford, because of course quite a few people have gone elsewhere. Barak Brinkholz is now in Seattle, Harvey Merritt at MIT, Biagio Lucchini is a lecturer at Swansea. So anyway, so there are people who have moved around, and the same is true, if you like, of the Pisa group, the Delbio, Opal, Panagopoulos, Rossi, Vicari, Campospini. There's been interesting work done there on large N. Then there's the Rutgers group, Narayan and Neuberger. And there's also quite a bit of work done on strings, not always with a focus on large N, but a more generally SU2, SU3s, SU4, but several groups by the Torino group have worked on that for a long period and done some interesting work on that. So those are some of the names and some of the people involved. in some of the calculations I'll describe. Sometimes I'll give references and sometimes I won't. Okay, let me just say a few words. You probably have heard something already about large N. So let me just say a few words about large N. As you probably know, that goes back to about 1974, at least large N in the context of field theories. Large N was used a little bit earlier in the context of statistical mechanics by people like Ken Wilson and so on. And indeed, I think our director here, David Wallace, was one of the early people involved in that. So, so that goes back to the sort of 74, early 70s. Tuft, well, the problem is with QCD is there's no obvious expansion parameter. You've got a coupling G squared, but if you fix G squared, that just tells you what scale you're looking at. So if you want to do an expansion in G squared, you need G squared to be reasonably small, and then that automatically means you're looking at things like very deep and elastic scattering. You can't discuss things like the hadron spectrum. That's the wrong scale. Coupling is not going to be small there. So there's no small expansion parameter, and Tuft had the very interesting idea that perhaps one should use instead 1 over n, where n is the number of colors as an expansion parameter, because n is 3, so 1/3 is already reasonably small. And then what you're doing is expanding around n equals infinity in powers of 1 over n. And as he showed, the leading correction, at least in the pure gauge theory, is order 1 over n squared, which is already quite a reasonably small parameter. So in principle, that's not a that might work. It might be a good idea. The problem, of course, as it became apparent, is that although SU infinity is in many ways simpler than SU3, it's not simple enough for us to solve it analytically. So we still don't know many of its properties. However, making certain assumptions, one can make qualitative predictions about the properties of SU infinity, in particular if you assume it's confining, then you can make a number of predictions about what will happen in SU infinity. And what one finds is there's quite a bit of phenomenology that you can understand in QCD, several things which are quite mysterious, like the OZI rule, as I point out down there, the OZI rule, and so the OZI, is there a pointer here somewhere? Ah, there it is. So several things like the OZI rule and the fact that you have narrow decay widths. Well, at n equals infinity, you have 0 decay widths and you have exact OZI, you have no mixing. So several features which are difficult to understand in QCD or in the observed world of the strong interactions become exact properties at n equals infinity. So you can, if n equals 3 is close to n equals infinity, that would explain why things are that way in the real world that we live in. So there are these, so that seems like an interesting limit to take. What do we know about that limit? Well, one thing that we know quite a few things about the limit, and I'll only mention a couple of things. One of the things we know just by looking at Feynman diagrams is that in order to have a smooth limit of that kind, we should take it with g squared times n being constant at large n, up to corrections of order 1 over n or 1 over n squared. And you can sort of see that by looking at this, the way a Tuft took Feynman diagrams involving gluons and broke them up into lines which are labeled from 1 to n, sort of fundamental. So you're labeling gluon by 2 indices, opposite arrows here. And so that you could do that by analyzing the vertices and so on of the gauge theory. And what you see in this kind of diagram, which is the gluon bubble here, is that, okay, so you've got these colors on the outside are fixed by the incoming and outgoing gluons, but then there is a sum over n here on this internal line. So you get a factor of n in such a diagram, and then you've got 2 factors of g. So this is of order g squared n, such a bubble. And if you want a smooth limit, what you want is that the relative weighting of Feynman diagrams should be the same as n increases, and that means the relative weighting of these bubbles should be the same, and that means that you better keep g squared n constant. If g squared n goes to, for example, if g squared n if you kept g squared fixed and g squared n became larger and n grew, that means that you would have that Feynman diagrams would all be of infinite order because the bubbles would have enormous weight. So you have to keep g squared n constant at large n if you want at least perturbation theory to have a smooth limit when n becomes large. So that's one of the things you expect that you will need to do in order to have a smooth limit at large n. I've also already mentioned the phenomenology successes of this kind of approach in terms of certain aspects of phenomenology, and these have been discussed by various people over the last 3 decades. Well, okay, I won't, as I say, this is not intended to be a review of large n gauge theories in general, but let me just mention a couple of things which are quite interesting before moving on to lattice calculations, which is my main topic. One of the amusing things about large n is that you have no, if you have confinement, then there are a number of things that you can say about the theory which basically arise from the fact that color singlets, in a confining phase you have color singlets, and it gets harder and harder to, if you like, the probability of getting a color singlet out of colored particles goes to 0 as n becomes large. Their sort of phase space goes to 0. Nonetheless, if you're forced to have a color singlets by confinement, you will of course have them, but then things become very simple in terms of their decays and interactions. For example, you would have, if you're having a decay of some meson, with quark lines here, the decay, if you look at this, you have some g here, and that's in the amplitude, and you'd have some g squared in the decay probability for these quarks going here. Now these quark lines are fixed by the initial quark lines, their color, and then if these are color singlets, this quark line its color is also fixed by these colors, and that makes that means you have no factors of n or anything coming from summing over colors, and you just have the g, and when you take the amplitude squared, the g squared. And so this is give you g squared, and that will be of order 1 over n if g squared n is fixed. So this is entirely because we're looking at color singlets. If our theory allowed all the colors, then of course you would have a sum here. When this thing decayed, it could decay into colored objects, and then you would have a sum over this n, and then you would indeed, it will be of order 1, basically. Your decays will be of order 1. So if you didn't have confinement, then, but you had bound states, particles would still decay at large n. But because you're in the confining theory, essentially the phase space for color singlets goes to 0, and they don't decay. And this can all be expressed in terms of the factorization of single trace operators at large n. So that's one of the, so you have 0 widths. I mean, particles have 0 decay widths at large n. They're completely stable, even your resonances, your row resonance. However, their interactions, the gluonic interactions, quark-gluon interactions within them, you have some valence gluons, and then you have quarks between them. Those interactions are still non-trivial, and you don't know how to calculate the masses of the states. And in fact, it's probably the case that something like the row meson mass isn't very different at large n than it is at n equals 3. So that's still an unsolved problem. Nonetheless, at the level of the color singlets, there's a lot of simplicity. And another simple thing, similar arguments to this, tell you that scattering, you don't have any scattering of color singlet states. And that's actually, of course, at n equals infinity. They don't scatter anymore. And of course, if you're interested in bringing in some ideas of integrability, that sort of suggests there may be a window there somewhere for bringing in some ideas of integrability into, at least into the n equals infinity theory, which you wouldn't be able to in the n equals 3 theory in the same way. These properties sort of arise from, also are related, if you like, to general factorization properties of color singlet operators. If these are traces here, individual single trace operators, then you can show, shown a long time ago, that the expectation value of products of such operators is equal to the product of expectation values with corrections which are of order 1 over n squared in the pure gauge theory. So basically at n equals infinity, expectation values just factorized like that, which tells you that if you're thinking of what that means, you have in terms of the Feynman path integral, it must mean that when n goes to infinity, you have just one field dominating the whole Feynman path integral, at least one gauge orbit, because one field plus gauge transformations. And this is called Witten's master field. And Witten's master field, if there is one field, since physics is translation invariant, if there is one field, then that field itself must be translation invariant. At least it may have gauge transformation, up to gauge transformations. So it's translation invariant. And if you have a field that is translation invariant, you can imagine that actually all the information is already there in any infinitesimal space-time region. And this has been, if you like, a sort of embodiment of that idea is the Iguchi-Kawai space-time reduction, which is originally on the lattice, and where you formulate the theory so that you get the same physics on a single space-time point at n equals infinity as you do in an infinite volume. So, and that goes back to 1982, these ideas. And they, although I'm not really familiar with this, I know that they have a sort of have become important in various areas to do with matrix models and so on. So this is an interesting set of ideas here. And so finally, let me also mention something else here. If you look at the Feynman diagrams of at large n, then there is an interesting way that you can put them together. This kind of Feynman diagram I showed you, a sort of bubble, you can get that, you can write like that. And if I have something like that, a planar diagram, I can write it in this double line notation, which shows me how color flows through the diagram. And I have 1, 2, 3, 4. I have g to the fourth. I have a factor of n for this, one, another one here, another one here, another one here. So I have g squared n all squared times n squared, which is the same order as this. This was obviously n squared. There's no g squareds here. So that's taking the fact that g squared n is constant. So all these planar diagrams are the same order in n once you put in that g squared n is constant. And if you think about how you can put them, you can imagine them being on a sphere where you sort of push this out, and all this is on a sphere with that circle at the back of the sphere, a little circle, and you've got little sort of polygons and things on the sphere, sort of planar, and you're putting it on a sphere in a planar way. Now, there's some diagrams that you can't do that to, and they're non-planar ones. For example, something like this, which, let me see if I can draw this, is always probably something like I'm getting I should have drawn this down, but there is a single something like that. Never mind. There is where this is a non-planar diagram, and if you look, there's a single loop here that I've drawn. It's a continuous loop, and it's g to the fourth. But now you only have this n from here and n from here, so it's that. There's two n's. And so it's down by n squared from this. So these non-planar diagrams are down by n squared from these. And you can classify, and if you think about it in the same way as I was suggesting this, so this can be on the sphere. If you try to do that with that, you have to pull out a handle here. So it's a sphere with a handle. And you can categorize these diagrams as being on surfaces of different genus, which just look like the kind of surfaces you have in a string theory when you have string scattering. Although these are vacuum-to-vacuum amplitudes, but you could have had things coming in, cylinders coming in, and did the same analysis. So you have this, so you can actually categorize, I'm saying things that most of you will know, I think. You can categorize all these Feynman diagrams in terms of the surfaces you can put them on, and the leading order n squared are the planar ones on a sphere, if I'm looking at vacuum-to-vacuum amplitudes. and then you're looking at ones with handles and so on, and it looks like the kind of thing you would get in a perturbative approach to string theory. Of course, these are really just diagrams on these surfaces. However, if you make G squared large, then these vertices that you've got on your sphere or whatever, the number of when G squared n becomes larger, then the number of the typical diagram will have very many more vertices, and so you become densely packed on these surfaces, and then it looks more like a continuous surface. Well, that's just a heuristic way of trying to say that it kind of looks like a stringy sheet. So back in the mid-70s, Atuf did suggest that n equals infinity gauge theory might look a bit like a string theory for these reasons. So that's an interesting way of, and that has been something that has been followed through by people like Polyakov and so on. Similar ideas have been developed by Polyakov, where you try to think of writing the gauge theory as a string theory directly. Then there is a more modern approach, if you like, which really goes back to Maldacena about 10 years ago, where you're looking to describe the gauge theory as a dual of a string theory. So the string theory is not directly the gauge theory, but it's a dual. There's a dual relationship, in that case, a strong to weak coupling duality, which is the subject, I think, of other lectures here, so I won't go into that. So those are two interesting ways of looking at the theory, gauge theories as a string theory. Well, let me now move on to the main subject of these lectures, which is the lattice, gauge theory calculations relevant to this particular topic. So let me say something about lattice calculations first, because with this, some of you are familiar, some of you aren't, but so I might as well give an introduction. So what are we trying to do here? Well, the lattice is actually just a tool. What we're trying to do is to set up our field theory in such a way that we can calculate Feynman path integrals numerically. If you want to so you're just going to do, you have this integral over all possible fields. The fields are defined over your space-time. A numerical integration of that is clearly impossible unless you turn it into a problem which has a finite number of degrees of freedom. Well, at least, okay. So, and the simplest way to do that is to take your space-time, and which of course has an infinite number of degrees of freedom, infinite number of points with fields on each point, and instead what you do is turn it into a finite number of points. So you've got to do two things there. You've got to first of all discretize it. So typically you take your Euclidean r to the 4 and you put it on a hypercubic lattice instead. And secondly, you have to put it into a finite volume. So otherwise it will still have a countably infinite number of points. You have to put it on a finite volume, and so typically one puts it onto makes it periodic, which effectively means you're putting it in a hypertorus. So what you're doing is you've got a 4-dimensional torus, and you've got a lattice which is on a 4-dimensional torus. That's your system. Now you've got a finite number of points. With some theories that may cause more problems than with other theories. However, one suspects that you should be able to do that quite well with gauge theories. And why is that? Well, first of all, the theory is renormalizable. So in some sense, what happens at very short distance scales doesn't affect what happens on longer distance scales, except through the variation of a couple of parameters, like the coupling, or a mass if you have it, the running coupling, the running mass. So the short distance fluctuations can be entirely, to a good approximation, absorbed into the variation of certain couplings. So that's easy to do. So that's why perhaps as long as your lattice spacing is much smaller than 1 Fermi, the typical scale of the theory, of the SU3 theory of QCD, you should be able to absorb it into couplings, and you should be able to get a good approximation. Secondly, as far as the finite volume is concerned, well, this is a theory. If you had massless particles, which of course at the classical level you do, but in the gauge theory. However, we know that as a result of a lot of dynamics, including confinement, you end up with a mass gap in the theory. And so given that there's a non-zero minimal mass in the theory, if you have a large enough volume, any corrections to the infinite volume limit will be exponentially small in the size of your volume, with something like if you have a box like this, and your mass gap, the correlation length associated with a mass gap is something much smaller, then the corrections will be of order e to the minus typically mg times L, if you like, e to the minus L in units of the Compton wavelength of this, with some constants, of course, and maybe some slightly different functional dependence somewhere. But basically, it's going to be an exponentially small once your length is large compared to the Compton wavelength associated with the correlation length of the system. So basically, we should be able to, as long as we make our lattice larger than a Fermi, whole volume quite a bit larger than a couple of times larger than a Fermi, maybe 2 Fermis, and as long as we make the lattice spacing, say 0.1 of a Fermi, something like that, then we should be able to do decent calculations, which are a good approximation to the continuum infinite volume theory, as long as we don't do anything silly in setting up our lattice action, if we take a sensible choice of a lattice action. Okay, so that's just general remarks about going on the lattice. How do we do it in detail? Well, it's rather straightforward. The usual degrees of freedom you have are the gauge potentials, elements of the SUN Lie algebra, and they basically tell you how to compare color at neighboring points, infinitesimally neighboring points in the continuum. Now, if we're on the lattice, our points are now a finite distance apart, so we need to have degrees of freedom that compare color a finite distance apart, and we have those in the continuum gauge theory too. What you do is if you take a path-ordered exponential of a gauge potential from x to x prime, then when you do a gauge transformation, it receives a gauge transformation at one end, g of x, and at the other end, g of x prime dagger. So that does the same job. And so this is the natural variable, kind of variable to use when you're discussing over a finite distance, comparing color over a finite distance. And so the natural thing to do on a lattice is indeed to put on the lattice elements of the gauge group, SUN group. And so what we do is we take, between every 2 sites, we have an element of the gauge group whose gauge transformation properties reflect those of the gauge transformation here and here. So these things on a lattice are called links, the things that join neighboring lattice sites. So these matrices here, these elements of the SUN group, live on the links of the lattice. And you assign them to the links of the lattice, and you give them, of course, labels. So here, for example, if you want the link that goes out in the mu direction from the site n, and since we have a discrete number of sites, we can label them by integers. So you would call that u mu of n, where this is the matrix, an n by n matrix, for example. So, so these are the degrees of freedom in the lattice. And as I just remarked, you want them to have these gauge transformation properties. So if you do a gauge rotation at each lattice site, g of n, then you want these things to transform like that, just like the path-ordered exponential of the gauge potential does if you give the gauge potential the usual gauge transformation properties you're familiar with. So, so these are degrees of freedom. These are the gauge transformation properties of these degrees of freedom. How do you get a gauge invariant action? Well, if you just take any product of these, ordered product of these matrices around any contour on the lattice, then all the gauge transformations along the contour will cancel out from each other from one link to the next, because the next link will produce a G of the same form. So that will, and these are SUN matrices, so G dagger is 1. Then when you take the trace, you can use the cyclic property of the trace to take the G at the end back here, where there is the G dagger at the end back to this G, and and that disappears. So it's gauge invariant. And this is, of course, just the usual thing you're familiar with the if you take a closed loop path-ordered exponential, then and take the trace of that, that's gauge invariant. And so for the same reason, this is gauge invariant. So if I take the product of these matrices around any contour on the lattice, closed contour, that will be a gauge invariant. That will be gauge invariant, and therefore that's a potential, something that could appear in the action. Because remember, the action, what does the action do? It compares the the action compares the values of the degrees of freedom at one point and neighboring points. In the continuum, they're infinitesimally neighboring, and so you have derivatives. But here we have a discrete distance, discrete minimum distance, and so we need something which has an explicit extent, like some kind of closed loop on the lattice. So any loop will actually do, but clearly in some sense the obvious ones to use are the very smallest loops on the lattice. That is to say, you take the elementary plaquette, here is an example of an elementary plaquette, 4 neighboring sites, and you take the product of these guys around here and take the trace, and that's a gauge invariant object that compares the values of a gauge of the degree of freedom here with its neighbors. So it's doing the right thing that action should be doing. And so we can take a sum of that over the whole lattice. So it will be rotation invariant because all rotations of it will appear, and translation invariant. So that's got the right space-time properties for an action, and use that. So just take the sum over all plaquettes of 1 minus 1 over n, real part of the trace of u of p. The 1 is just a convention. It's convenient. It's convenient because if I write it this way, any constant here would cancel out when you do any calculation, because you always take partition, some expectation value divided by this, and so any constants would cancel out. But the reason it's conventional to use this constant is that the maximum value of this object is 1, and therefore the minimum value of this action is 0. It's non-negative. It's greater than or equal to 0. That's a convenient value to have. So here it is e to the minus s. Now, this is a gauge invariant object, but so is any constant multiplying it. So let me just put it in a constant. I don't know what that constant is. We'll have to decide in a moment what that constant is. And we have we integrate over the using the sort of Haar measure, standard Haar measure for group, which has sort of natural properties of a measure that you would want. The Haar measure, we integrate over these group elements on each link. So we integrate over the group elements on each link, and we weight them with this exponential. And that's our Euclidean Feynman path integral on the lattice. Okay, now it's more or less automatic, since we've built in gauge invariance and enough space-time symmetry. It's more or less automatic that if the lattice spacing goes to 0, we will recover the usual action. And of course, we'll have higher order operators, but they will be multiplied by higher powers of a squared, and a goes to 0 when we take the continuum limit, and so those will vanish, and we'll be left with the leading piece, which is the usual action. So that's what you would expect. And indeed, I won't go into that, but that's what one finds when one does it more carefully. So we expect that this would go to that in the continuum limit. And that already tells us something about this parameter beta. This parameter beta will have to go to something over g squared. So we can write beta as 1 over g squared. The something turns out to be twice the number of colors when you do the analysis carefully. And you're dividing by g squared. Now, what is this g squared? The g squared here is the bare coupling. So it's one possible definition of a running coupling on the scale at which you're defining your degrees of freedom. The degrees they're being defined on the scale of the lattice spacing. So it's a definition, one possible way of defining a running coupling on the scale of lattice spacing. And I would just therefore call it g squared of a. It's a running coupling at the scale a. So now you know where the continuum limit is, because when a goes to 0, the running coupling goes to 0. It's an asymptotically free theory. And therefore, beta goes to infinity. So in order to go to the continuum limit, you tune beta to larger and larger values, and you head off towards the continuum limit. Of course, we never get to the continuum limit. What we will do is we will do calculations at some set of values of beta, separate calculations with different values of beta, calculate, for example, the mass spectrum, and then take the continuum limit of that mass spectrum. And at some point, we won't be able to go any further towards smaller a or larger beta, simply because of the constraints I already mentioned, which is that your volume has to be bigger than, say, a couple of Fermis. And as your lattice spacing goes to 0, that means that the number of sites you have goes to infinity. So the number of sites, if you want the number of sites, if you want your lattice to be 2 Fermi in each direction, then the number of sites you have is 2 Fermi divided by A in Fermi units. So that's the number of lattice sites you have. And the total number of sites will be that to the 4th power. So, if once my A is, say, 0.1 of a Fermi, I already have 20 lattice sites in each direction. Total number of lattice sites is 20 to the 4. I've got these matrices sitting on each one of these links, and there's a large number of them. You're getting close to 1 million links, and then you're going to have to do some numerical calculations, so it all takes time, even on a computer. And if I try to make the lattice spacing 10 times smaller, I'll be talking about a lattice which is 200 to the 4th, and even, well, people are getting to do lattices of 100 to the 4th, using the very largest computers you can, but for pure gauge theories. But there's no reason to push it that far because, as I say, because of the renormalizability and so on of the theory, you can do reliable continuum extrapolations with lattice spacings that are more like 1/10 or 1/20 of a Fermi, as we'll see. Okay, so that's so at this stage we've got things set up to do a calculation on a finite system, and now we do a Monte Carlo, which I'll say not very much about. So basically, with the purpose of the Monte Carlo, here you've got a path integral. This is still a genuine path integral, which is a integrating over group elements on each link. And although these groups are compact, nonetheless, that's an infinite amount of work still if you want to do it. So instead, what you do is you pick some typical field configurations. So what the Monte Carlo does for you, what it does for you is it's rather like if you had an integral over x of just a real valued variable from 0 to 1. You might do that numerically by picking a number of points between 0 and 1, evaluating the integrand there, and just using that as an approximation to the integral. And you do the same thing here. You pick a number of gauge fields, and they will give you an approximation to the whole integration space. Now, you can't just because the integration space is so large, you have to do a bit better than just picking the points at random. And what you do is you pick your gauge fields. You might pick a few thousand gauge fields to approximate this integral. Each gauge field is what does a gauge field correspond? The gauge field corresponds to picking some particular matrix on each link of the lattice. So you've got some SUN matrix on each link of the lattice, and that gives you one gauge field. So your Monte Carlo is trying to produce for you a few thousand gauge fields that will give you a good approximation to this integral. And the way it does that is by producing those gauge fields with this measure, not just with this Haar measure, but with this exponential as well. So you can do that. You can pick your gauge fields so that they have this distribution to start with. They're uniform in with this measure and not uniform with just this measure.
How come the exponential doesn't appear on the right-hand side of the bottom formula? If you were doing what you said, you'd pick a series of random points and evaluate the whole integrand.
That would be true, but as I was just saying, what you actually do is not that. You pick them with this measure, with this exponential included in the measure.
Ah.
So that actually makes it more difficult, obviously. So that's the way you do the Monte Carlo. That's the Monte Carlo aspect of it, is that you actually build in this into the measure with which you generate these fields. So in fact, this is actually in the measure, and it's only this thing that you calculate, whatever you have there. Yeah. Now, although that sounds as if it might be difficult to do, it's not too difficult to do in the case of, say, a pure gauge theory, because the gauge theory is local. So when I look at this action of mine here, and suppose I look at one particular link matrix, one matrix on a link, that is only appears in a few plaquettes. It only appears, if I'm looking at this link matrix, it will only appear in, so if I'm looking at a particular, let's call the link L, then it appears in the action in these plaquettes and another set of 2, which I can't draw because there's 4 dimensions. And this is in 3 dimensions it will appear in these plaquettes. So there's 4 terms here, but there's six plaquettes which actually include this. The rest of the action doesn't care about the value of UL. So when if suppose what I do, and this is what you do, suppose I generate my gauge fields by looking individually at one link matrix, then picking a new value for it. So I pick a new value for the link matrix, and I want to pick it in such a way that it will have this distribution. All I need to do is to make sure that it has the distribution e to the minus beta with this sum of 6 plaquettes. And there is this UL. Then there is a product of 3 other matrices, which I can call Xi, I, and there's 6 of those. So there is, and then I take a trace. So basically, this weighting here, exponential of the action, will look like, well, there's probably not there's probably a plus here because there's a, it will involve only the U of L, the matrix I'm looking at, multiplied by a sum of other. Each one of these is an SUN matrix, so these Xi's, because it's a product of SUN matrices, but there's a sum of 6 of them, and they're no longer an SUN matrix. Nonetheless, you can see that this is not, this is not an impossible problem. You could imagine being able to solve this problem, and indeed it has been. And so you can actually generate, ULs with this. For any Xi, you can generate it with this distribution. So what you do is you start off with some gauge field, which can be a completely random gauge field or one which is completely trivial, where all the matrices are unit matrices. And then you start applying this Monte Carlo algorithm, which consists of saying, I will take one link, which originally is a unit matrix, and then I change it using to another link, UL to UL prime, along this link, with this kind of distribution. And then I've got a new gauge field where all the links are the same as they were before, except this one. Now I go to another link. So let's say a neighboring one. Doesn't have to be a neighboring one. And I look at this one, and I do the same thing. I change that using its neighbors as its kind of heat bath. This looks like a kind of heat bath for these links here. And the neighbors now, of course, include the one I changed before. So it's got a new value. That's part of so it's an iterative process. And this will now have some new value. And you keep going through the lattice. You go through the lattice, and you change every single link matrix that way. There may be 1 million links, and you change every single one with this kind of distribution, which depends on the values that its neighbors have, because that's through the plaquette. And you update the values of the plaquette all the time as you change links here. And at the end of that, you have a whole new gauge field configuration, which is still correlated with the original one, because it knows about what the original one was. However, if you keep doing that process on and on, then eventually you will have a distribution of gauge field configurations that have the right weighting here that you desire. So with the gauge theory, you can do this. If you have fermions, and I won't be discussing fermions, so I don't really have to say much about that, but maybe it's worth just remarking, with fermions it's a little bit more, it's more difficult, because with fermions you would have up here Grassmann variables as well, an integral over Grassmann variables. They appear quadratically in the action, which is nice, psi bar d slash psi. And then what you do is you integrate. You can't toss a coin with Grassmann variables directly, so you integrate them out, and you get a determinant. So you get a determinant of the Dirac operator, and that you can then put up in the action as a log determinant, but that's kind of non-local operator now. So now you have to do things differently, and I won't go into that, partly because it's not my, well, it's another story.
This topology, will you get to it?
Yeah, so that's an interesting question. Of course, this will only work if the algorithm is ergodic, that is to say, it can explore the whole phase space. Otherwise, you'll end up generating fields which are on some corner of this integration space, and you won't have the real integral. And as you say, an example of the sort of thing that you might worry about is topology. Here, gauge fields have topological charge. So in principle here, there's a sum over all possible topological charges as well, gauge fields with all possible topological charges. What I've just described to you, the algorithm I've just described to you, sounds almost like a continuous deformation. I mean, I'm looking at one link at a time and making a change in one link at a time. So it's pretty much as close as you can get to a continuous deformation if you're on a lattice. Now you know that sectors of different topological charge, you can't go from one to another in the continuum by continuous deformations. So you might wonder whether there are barriers here in the algorithm which prevent you from going to from one topological charge to another. Now, actually, the answer is, at a finite lattice spacing, no. And what happens? You change topology in the following way. So you can imagine you've got some topological charge and you want to change it by 1 unit. So what has to happen is that gradually there is an instanton, say. Let's call it an instanton, since that's the only kind of topological description we are readily familiar with. So you have an instanton, which is, say, typical size, whatever it is, a third of a Fermi or something sitting there. And then what has to happen as you change the gauge field, the instanton can start to shrink, the core of the instanton. So the core of the instanton, in SU2 at least, the sort of typical gauge potential is is it x squared over, anyway, g of x, where this is a particular gauge transformation which has unit winding. So if x becomes large, this is at large x, this is just 1, and you've got just this pure gauge. When x becomes smaller, it's not pure gauge anymore because of this factor, if I remember this factor correctly, but it's something like this. And so you have the core of the instanton where ff dual is non-zero and trace f squared is non-zero. Now imagine that core changing rho so that it gradually shrinks. At some point, when rho becomes less than a lattice spacing, the core shrinks out of the lattice, and all that you're left with on the actual lattice sites is something where this is 1, and so it looks like pure gauge. It's a gauge singularity. So you can actually change the topological charge of gauge fields on the lattice by shrinking an instanton out of the lattice. Now, whether that actually, how efficiently that happens in terms of ergodicity and so on, how efficiently that happens depends on the probability of this process. But it is non-zero, so in principle it can happen. And it does happen in typical calculations. As you make the lattice spacing smaller, it becomes increasingly unlikely. But that's an aspect of one aspect of what's called critical slowing down as you approach the critical limit, as you approach the continuum limit. It's a general problem that what we're doing here is we're putting in fluctuations on the scale of the lattice spacing. And as the lattice spacing goes to 0, the distance between the size scale of the lattice spacing and the size scale you're interested in, which is 1 Fermi, becomes larger and larger. And the influence of the changes you're making becomes smaller and smaller on the infrared degrees of freedom. And so the whole thing kind of grinds to a halt. But typically we never get that far because our lattices would be too large anyway if we try to do that, and so we haven't been doing calculations of that kind. But the calculations we have been doing, we do have, we can change topology. Of course, the change of topology, as I've described it, is a lattice artifact. It shouldn't happen in a continuum if you do continuous deformation. So it's using, if you like, a lattice artifact to explore the full space of gauge fields. But that's an interesting question, which I might get back to when I discuss topology. So the bottom line there is that you do a Monte Carlo where you generate fields. So suppose you want to calculate a Feynman path integral of this kind. Whenever you're doing an expectation value, of course, there would also be a 1 over z here, but let me forget about that for the moment. So you just have this integral here with some arbitrary capital phi, and which is a function of the u's. You want to calculate this expectation value, and what you do is you take your fields that you've generated, and you just calculate the average value of this operator phi for those fields. You know, you've got a set of fields with explicit matrices. Phi will involve some closed loops, presumably, of these matrices, and you just calculate it for each gauge field. You put in the particular fields, particular matrices you've got in that gauge field. You calculate phi for that particular gauge field, capital I, and then you average this value. And because this is a kind of statistical process, you would expect this to have errors which are order 1 over the square root of the number of gauge fields that you've got. And typically, you might have 100,000, 1,000, a million gauge fields, depending on the problem you're looking at. So that's the introduction, if you like, to lattice Monte Carlo in general. And let's now look a bit more in detail about how we might calculate masses within this framework. I've been talking about masses, so let me say something about how to calculate them in such on a lattice. Well, to start with, how would you calculate them generally? In general, in a Euclidean space-time? Well, one simple way, and the way we'll be doing it, is to just look at a correlation function of some operators at different times. So you have some function of the fields here at one time, time 0, and at another time t. These are Euclidean times, and you're on a lattice, therefore the time is a certain number of lattice spacings. So it's a times the number of lattice spacings that you've got in between your two operators. So nt is actually the thing you know. You don't in advance know a. All you know about a is that it's 1 in lattice units, but you don't know what it is at this stage, what it is in physical units or anything else. That's what we will learn once we do these mass calculations. So you've got these two operators, and basically what you're doing there is calculating a correlation between the way the fields are fluctuating at time 0 and at time t. And the way they fluctuate, there's information carried between those points, and the information is carried by exponentials in the various masses of the theory. And you can see that by if you pull out the Euclidean time translation operator, assume the vacuum has 0 energy, so the corresponding one here is 1. You just have this, and you have put in your complete set of energy eigenstates here, and you will get this representation, this standard representation for this kind of correlation function. So sum of exponentials, where you've got up here the energies, you're summing over the energies, and you have here the time, and the time is the lattice spacing times nt, and I've put the lattice spacing now here. Nt is what we know, and so if we now calculate this numerically for different values of nt, we can extract the energies, but we always extract them, of course, in lattice units, because this is the number we can extract. We see some exponential as a function of nt, and the exponent will be a times the energy. And if you go to large T, you will expect, well, when you go to large T, the lightest state the lowest energy state should dominate, simply because the others have faster falling exponentials. So as you go to t equals infinity, you can extract from the final single exponential. So you go to large T, your correlation function will fall off as a single exponential, and you can extract the lightest mass. So let me just say, so the question is, how well can we do this? There's no point. I mean, what we will want to do, actually, it's clear what we need to do in this kind of in this set of lectures, at least in the beginning of these lectures. We need to calculate our lattice, our masses accurately enough that we can then do accurate continuum extrapolations to the continuum limit, extrapolation to the continuum limit, and then we can compare these values, and they have to be accurate enough so that when we compare them for different values of the number of colors, we get a meaningful comparison. You don't just have very rough numbers you're comparing. So that's so clearly the accuracy is all important here. So is it possible to do accurate calculations? Well, first let me show you that it is by showing you an example of a typical correlation function from which we extract masses. And here is a correlation function. So what we're looking for, remember, is if you see a single exponential, that means you're seeing all the other excited states have died out, and you're seeing the lightest state that communicates with that operator. So here, what we have here happens to be SU3, on a 32 to the 4 lattice at what happens to be the smallest lattice spacing at which I've done calculation. So you're the closest to the continuum limit, at least the closest to the continuum limit I've ever got. Other people have got a bit closer for other problems where it's important to do so. So this is a relatively small lattice spacing. You'll wonder how I got the Fermis here. That'll become clear later on. At the moment, I'm just trying to give you an indication of what is the lattice spacing in this calculation without telling you how I got this value. It's sort of, well, yeah. So here is the correlation function. It's the sum of exponentials. And what you can see in this correlation function is that it almost immediately becomes a single exponential. It's not quite a single exponential. There's a slight deviation here. So if you like, the overlap of this operator I'm using here onto the lightest glue ball state, which is what I'm calculating here, the lightest scalar glue ball state, in fact, is J equals 0, positive parity, positive charge conjugation state. That overlap is about 95%. So it's a very good wave functional. The operator we're using is a good wave functional for the glue ball. And you see this very nice single exponential, and unambiguously that it's single exponential. It's not quite, I keep saying exponential, but remember we are on a torus, or torus also in the time direction, so actually we're dealing always not with exponentials, but with coches. There are two exponentials depending which way you go around the torus. Your transfer matrix can go this way around the torus or the other way around, and the two together give you a cosh. So in the middle it sort of bends over the correlation function. But for all practical purposes,
Increase as you go to larger and larger times. Just because the signal is smaller.
Yeah.
Stays the same.
That's right. That's an important point. For this kind of calculation, the signal obviously becomes smaller in the sense it's dropping exponentially.
Yeah.
However, what about the errors? Well, the errors themselves, if you ask what is the error, I'm looking at some correlation function. And the error is related to the square of this. The expectation of this minus the expectation value of phi dagger phi 0. So the fluctuations of this operator are given by this. This itself is a correlation function. And if you look at this correlation function, although it's not immediately obvious, if you look at it at various channels, it does have a vacuum in one channel. So this correlation function, although it may show some t dependence, is essentially at large t a non-zero constant. So the error is going to be a non-zero constant at large t, while my signal is dropping like a stone. And so the relative size of the error to signal becomes large on this kind of plot. But that's and this depends on the calculation. In some calculations, this may not have the vacuum. I mean, in some hadron spectrum calculations of, say, things like the rho mass, you will find that the lightest state in any of the channels is not the vacuum, but say the 2 pion state, and then that will also be dropping exponentially. And there you have a much better error to signal behavior. You would have small errors even at large times. But here, in all the pure gauge calculations I will be describing, this is a common feature, that the errors grow with t. And that's quite important. That's actually very important, because what it tells us is that if we're going to be able to extract a mass, we have to do it from small t. By the time we get to large t, the errors are too large. So we have to do it here. And in order to be able to do it here, in order to have our exponential here, single exponential dominating here, we need operators that project very well onto the state we're interested in. Otherwise, you will have something from which you cannot extract a mass. And in fact, you may wonder how it is that one has got such a good operator, and that's a good question to which I will turn to in a moment. So let me now show you what happens if you use an obvious operator rather than the operator I use there. Now, what is the obvious operator you might use? We want to do a 0 plus plus glue ball, so we want an operator which has the same quantum numbers as that. First of all, obviously we want a color singlet operator, and what is the simplest color singlet operator we've got? It's the one we've got in the action, the plaquette. So let's take the plaquette, label it by P. So that's a trace of these guys going around here, of the matrices going around the boundary of the plaquette, and I'll call this UP. And then if I take a sum over all plaquettes, that will be rotationally invariant. It's all possible rotations, so it's the nearest thing to a spin 0 on a lattice. Of course, we've only got 90-degree rotations on a lattice, but that will be where the spin 0 object will appear. And it will be a rotation and translation invariant as well, because we've summed up over all translations. So we've got a nice zero momentum rotation invariant operator, which is a color singlet, and which sounds like a good operator to start using. So what happens if we use that operator and calculate its correlation function? So this is, what I had just now. And if on the same calculation I take what I get from that, I would get this. So this is not very useful at all. You might think, well, maybe I'll extract a mass from here, but then if I do it from here, I get a different mass, and then I've lost the signal. So I've got nothing there. And this is, a rather expensive calculation, a long period of time, big lattices, and you get nothing. And so this is what you get with a simple operator. And the reason this is happening is if you think about this operator, this is the equivalent of using trace f mu squared in the continuum. It's an operator which, because it's essentially point-like, is a point-like operator, it will project more or less equally on all states, including excited states. I mean, if you want to project onto the lighter state preferentially, what is the lighter state? First of all, the lighter state is extended. It's about 1 Fermi or half a Fermi across, whatever it is. It's some extended. Presumably, it's quite smooth. The more non-smoothness you have, usually, the more energy you have. So in the classical case, Schrödinger equation stuff, you have nodes in wave functions, excited wave functions. So if you think of nodes, if you have a large smooth operator, then if you have an excited state which changes sign, when you take the projection, it will tend to cancel. While if you take this point-like operator, it doesn't see the change of sign. It's just poking around in the wave function at various different points. So to a first approximation, you have an equal overlap onto all the states. That means the overlap onto the particular state you're interested in, the lighter state, is extremely small. And so you have to go to very large times. You would have to go to very large times to see it coming out as an exponential. And of course, we can't get to very large times because this has disappeared before we get there. On the other hand, if you have an operator which projects well onto light states, you can get something like this, where it doesn't project well on these ultraviolet excited states, but it does project well on the state you want, and you can extract a mass at the level, as you can see. Here's an extraction of mass. This is the level of around 2%. So,
what operator was that, in fact?
Yeah, it sounds as if we've got a global wave functional, and here it is. This is what you would like, a global wave functional. Unfortunately, it's constructed in a way which is so what we try to do is, what one does is construct a smooth operator. There are two aspects to this calculation. The sort of less important one is using a variational. So you have a lot of operators, and your basic, in your correlation function, what you have is e to the minus h. So this is very much like if you were doing in quantum mechanics variational calculations, you would look over bases of operators which minimize this quantity. Here we will be looking over things which maximize this quantity, e to the minus h. And that means maximizing the correlation function at some distance. So we've got a set of operators, and we look at the linear combination that maximizes it. That's a variational aspect. But that's no good if none of your operators are any good to start with. You need some good smooth operators. And to construct the good smooth operators, that's done by, well, it's basically done by some iterative procedure. You start off with your link matrix, and then you try to make it a little bit smoother by adding to it these path-ordered exponentials here. So now you've got something which is a little bit smoother. And then you take a product of that. And now you've got something which extends over two lattice spacings. And then you iterate the procedure by, at the next step, using these guys in smoothening this kind of smooth operator to make it even more smooth and end up being twice as long, 4 lattice spacings. And you construct closed loops out of these things. And if you sort of count, if you do that 3 or 4 times, because it's an iterative procedure, And if you count the number of elementary paths that appear in a closed loop of something like this, which has been iterated 3 or 4 times, you get, it's like 10 to the 60 closed paths. So it's a very fast way of producing very smooth operators. So these are the operators that have been used. And there's a basis of operators which depend also on the kind of closed loops you construct out of them, and also on the amount of smoothing that you've done. So it's a relatively fast procedure. If you try to do it explicitly, constructing a lot of paths, you would get nowhere. But doing it iteratively, you get there quite fast. And it turns out that the intuition is that what you need is basically a smooth operator, and that turns out to work. Then once you've got this smooth operators, you've got your best smooth operator, you look at your basis of operators, and you look at that part of the basis which is orthogonal to that best operator you've got for the ground state. And then you repeat the variational calculation there, and you get your operator for the first excited state. And so you can get excited states. That works pretty well. It's not as good as this because, this whole idea was based on the idea of having a very smooth wave functional, and you've aimed at getting the ground state. So there's been less work done on getting excited states, but they can be obtained to some extent, actually. Well, okay, so that's probably a convenient time for me to stop this lecture. I think it is time, isn't it? Yeah, cool. So I don't know. We'll continue through this program of what we learn about large N tomorrow.
Any questions for Mike?
You mentioned very early in this large N expansion this Iguchi-Kawai reduction, and you still have only one gauge orbit. Does that mean that in large N theories you wouldn't have any instantons or something like that? Or?
I don't really know what happens to instantons at large N. Again, they're kind of localized objects, and you don't have instantons. Certainly, don't have instantons in the same way. Somehow, this is the chap you want to talk to, or Pierre Van Baal over there. Definitely Pierre Van Baal. But it's actually not. Well, I don't want to spend too much. The instantons, there's a classic argument that instantons become unimportant at large N. I think Witten first published it, which is your instanton, amongst other things, has a e to the 8 pi squared over g squared. And if I put n in there to make this constant, then you've got an exponential suppression with n of instantons. So isolated instantons disappear. Now, of course, this should be a rho. And when you look at larger instantons, this becomes smaller, so this factor here becomes smaller, so it's less clear. There's still an exponential suppression, but it's less clear. You've got a large instanton. And then you've got a big factor here from the number of ways to stick an SU2 instanton in SUN, and that grows exponentially with n as well, but not enough to kill this. But if the instantons are overlapping, then you can change even this. The whole thing goes out of control. So you don't really know what happens to overlapping instantons, but I'm not quite sure what an overlapping instantons are anyway. That's a sort of more difficult question. Certainly isolated instantons disappear, so we don't have to worry about them at large N. But what happens to topology at large N is an interesting question which I don't know the answer to. We know from the lattice some things about the topological fluctuations of the topological charge at large N, but not. But actually, in terms of understanding what is happening to topology, that's more tricky. I'm not sure if I can answer that.
Further questions?